postbag, and it's fragile. And from China, of course. Yeah, well. And for fragile things, it's really, really nicely packed, unlike the LCD displays I received lately, which were not packed at all, at least half of them. Yeah, card link. Yeah. Okay, that is, I mean, for a few, 1, 2, 3, 4, 5 little boards, 2 layers of foam, it's a little bit excessive. Yeah, let's go a little bit closer and have a look at that. So I already think I know what they are. Yeah, they are. They are little boost converters. I mean, really little. Let's get some measurements. So that critter is, and I should zoom out just a wee bit, I guess. So yeah, let's call that 17.5 millimeters. Imperial here somewhere or down there. Let's call that, yeah, 37. 37? Yeah, 37. I'm not going into the 10th, really. And the height is, yeah, let's get those pins with it. So overall, okay, you could cut that down a little bit, but let's say height 7.5. Anyway, if you solder in some pins, like I did right now, you can fit that neatly on a breadboard. The pins are apart 1.2 inch and in this direction 0.3 inch. So yeah, the holes are a little bit too big for headers, but yeah, you can make it fit. I guess they are so big so that you also can yeah, feed in a cable or something with ease. Yeah, let's get a close up of that thing, huh? I mean, there's not much on it. So I have my macro lens in. So let's first start with the potentiometer, which is not a Born's, but a Bonan's, but it certainly looks like a Born's. And it's 1, 0, and 4 more zeros. So 100K, am I right? I think so. We have a little resistor here, 222, so that should be 2.2K. Yeah, 22 and 2 zeros, 2.2K. Yeah, we have little inductivity, of course. It's a boost converter, 220 microhenry. We have, sorry, can I get a focus? A Schottky diode, SS34. 2 mystery caps here, ceramics, and a mystery Chinese controller chip. This might be a little bit hard. Oh, XT1200, yeah, trying to get another angle, 28, 1208 or 120 smear, 1200, yeah, something like that. I have to look that up. And well, that's all. And no, there's absolutely nothing on the back. The marking on the chip could refer either to a SY7208 or to a TCS9300. I only found data sheets for SY7208, that one from Sylogy, high efficiency 1 MHz, 2 amps, step up regulator, yeah, seems to fit the bill. Later. Anyway, the typical application, yeah, exactly what we saw. The 22 microhenry inductivity, the 2 capacitors, and this fixed resistor network here for the feedback is of course the 1 resistor and the potentiometer. Yeah, the Schottky diode, and you can forget about that pin. SS is for soft start. You don't have actually to connect it. So yeah, you can cheap out here, which they did, of course. But there's a little problem here. The out pin, absolute maximum rating, is only good for 26 volts. And the input voltage range is 3 to 25 volts. And if we put that all together, we see some discrepancies between the description on Banggood and yeah, the datasheet of that SY7208. So input voltage should be 2 to 24 volts. I would have loved if that thing worked with 2 volts, but that chip wouldn't. And of course, maximum output voltage, they say recommended for use in 26 volts, and absolute maximum rating was 26 volts. So yeah. And the dimensions were also off, so we have missing 7 millimeters here, and they added that to here, and then yeah, it's about right. So we won't fuss about that. Okay, but what the thing can actually do, yeah, I have to test that, and I will. But maybe we should get the listing out of the way first. So that was a pack of 5 of these, and yeah, it looks the part. Step-up converters, DC boost converter, 2 amps, blah blah blah, 2 to 24 volts to 5 to 28 volts, adjustable. Yeah, we'll see. A total of 352, free shipping. So nice. I did a whole lot of measurements, almost 40, and killed one of these thingies in the process. They're really serious about input voltage needs to be lower than output voltage. That thing dies if your input voltage is higher than your set output voltage. And yeah, I will put that in a separate video, which I upload at the same time. And will directly go to presenting the results. Anyway, I did over 40 different measurements, and of course I prepared an Excel spreadsheet. So my first use case was I wanted 7 volt output to feed into an Arduino power pin. And I'm using 3 AA batteries to do that. So with the AA's empty, I have 3 volts input voltage, and with the AA's full, 4.5 volts input voltage. And yeah, the voltages here are also in the range for your lithium ion or lithium polymer aficionados, I guess. Anyway, with 3 volts input, I can get out a maximum current of 150 milliamps. And the efficiency is actually surprisingly good. So at the outer ends of the scale, 78%. And here right at the sweet spot for that particular DC-DC converter, 90%. And of course, if I draw out 150 milliamps at my output, I have to put in 450 milliamps. And yeah, out of my head at 200 milliamps, you empty a AA cell in less than 2 hours. So yeah. At 4.5 volts, yeah, all efficiencies are above 80%, so 86, 93%. That was actually the value advertised in the datasheet for that thing, datasheet. Great efficiency greater 93%, and actually in in some cases you can reach the 93%. So efficiency is up to 93%. But yeah, if your power requirements are not too big, between 50 and 100 milliamps for your Arduino, for example, yeah, you can run that on 3 AA's. Yeah, 4 AA's, so empty 4 volts, full 6 volts. Yeah, similar picture. Yeah, getting 200 milliamps out requires 400 milliamps in. That's maybe a little bit beyond what a AA can do, but yeah, 100 milliamps, 150 milliamps. The input currents are below 200 milliamps, and so yeah, you might run your AA for 10 hours or so, which is not great, but okay. Just to be complete, if you want to feed the 5 volt rail of your Arduino directly, of course we cannot use 4 AA because it's a step up converter, and putting in 4 full AA's is an input voltage of 6 volts, so we can use at most 3 AA's. Yeah, 3 volt empty, 5.4 volts full. Efficiencies are also okay. Yeah, no problem there. And you are able to draw out also, let's say, between maximum 150 milliamps. I tried the 200 milliamps, but yeah, that's borderline. You see that also at the efficiency value and the input current. So that DC-DC converter was really struggling there. But yeah, supplying directly 5 volts, 150 milliamps from 3 AA's, it's possible. We should also have a look at that measurement series, which was not included in the spreadsheet because I was just trying out what input voltage that thing actually needed. The datasheet says 2 volts minimum input voltage. And at 2 volts I was not able to getting out with a 7 volt output 10 milliamps. I needed 2.1 volts. Okay, 2.2 volts, all 7 volt output. I could get 20 milliamps out. At 2.3 volts, 50 milliamps, 2.6, 100 milliamps, and 3.0 volts, that's over here. Actually 150 milliamps, and at 3.8 volt input 200 milliamps, all at 7 volts. And generally my impression is that thing is not really characterized, and you have to test what increase in voltage at what current is actually possible with that thing. And talking about feeding directly 5 volts to the Arduino power rail, we should have a look at the quality of the voltage coming out there on the oscilloscope. Have a look at the ripple and such. So let's start by starving our boost converter. I adjusted it for 5 volts output, and it can't deliver 5 volts because my input voltage is only about 2.7 volts, 2.6 volts. And your output only AC coupled looks something like that. And time constant here is 1 millisecond. It tries to run, then it stops, it tries to run, then it stops, it tries to run, then it stops. Now we are a little under 3 volts, the voltage where it should be able to deliver 5 volts, and it does deliver 5 volts at 150 milliamps. And let's have a closer look at that waveform. So we have here something not quite a sine, but something like that, with a frequency of about 30 kilohertz and about 600 millivolts peak to peak. And overlaid to that is something about 1 megahertz with a whopping 1.8 volts peak to peak. We're not running that thing probably. We are still starving it a little. So let's give it a little bit more input voltage. At 3 volts input voltage, what our test case was, 5 volt output, 150 milliamps, it looks much better. But we still have that grizzle here, that 1 megahertz grizzle. And that 1 megahertz grizzle is of course the switching frequency of that thing. Okay, you couldn't see it down there, that thing. And when it's now running within the specs, this is still 1 volt peak to peak, which is a little bit much. At 4.5 volt input voltage, so 3 AA batteries, and I switched over the scale, so 25 volts full scale, 5 volt output, 150 milliamps load, it looks a bit better. And time scale wise, I zoomed in here now, so one line is 1 microsecond, so that's pretty much 1 megahertz, maybe a little bit less, maybe 900 kilohertz or 950 kilohertz, but we still have the switching noise here of a good 800 milliamps peak to peak. So with no load, 0 milliamps, things look a little bit better. Remember, no load, and I'm now down at the time scale to 100 microseconds, and 120 millivolts per unit. And what you see here is about 120 millivolts peak. And yeah, a lot of noise, of course. It's a switching power supply, but you can, yeah, you see how it's working. Just for fun and verification. 3 volts input, no load, and my timescale is now 10 nanoseconds. So you can see, yeah, the charge discharge action on the output capacitor in detail. But yeah, for measurement, let's go to 1 microsecond and have a look here. Yeah, that's still a good 100 millivolts peak to peak noise, which is not so bad. The problem is at 3 volts, 150 milliamps, that noise here, 1 megahertz noise of 1.8 volts peak to peak is, yeah, unacceptable. Let's see if we can do something with a little. I think that's 470 nanos ceramic at the output. And indeed, another 470 nanofarad output capacity, that little thingy here, helps a lot. Switching noise at the output is down to, let's say, 500 millivolts peak to peak, which is also what you get with very cheap DC commercial, so not from Banggood or China DC-DC converters, the very cheap ones. I would prefer 200 millivolts peak-to-peak noise on the output, but yeah, I guess you will have to do more filtering. So that's it for today. Yeah, mailbag and review and test and characterization of that little boost converter here from Banggood. Well, you have to take it for what it is. Dirt cheap boost converter with the minimum amount of parts, and the parts being the cheapest available. So yeah, these things definitely have some drawbacks. They basically work within their limits, as we have seen. You can really easily destroy them by supplying an input voltage higher than your adjusted output voltage. Yeah, that was within a few seconds. It made noises, the one I killed, and then it was gone. Yeah. But yeah, for a small project, probably add some more output filtering. You can drive without any problems an Arduino. Or at 7 volt outputs, yeah, you can also drive an Arduino. Yeah. Bye.